Okay. So, yeah, good evening, everybody. Today's speaker is Jim Thomas. He is a postdoc at the University of North Carolina at Chapel Hill in the Department of Maths. And before this, he was postdocing in the Woods Hole Oceanographic Institution and the Department of Oceanography in Dalhousie University. He spent some time at Cambridge as David Crichton Fellow, and then he did his PhD in the Courant Institute of Mathematical Sciences in New York University. We look forward to his talk. So the way it's going to work is that if you have any question, Jim is happy to be interrupted and ask the question during his talk, and he will take questions at the end as well. So over to you, Jim.
Thanks a lot. Thanks a lot for the opportunity. I'm looking forward to everyone's questions and thoughts on this. So this is work I did with collaborators Oliver and Schaefer at NYU. Ray was a former postdoc at MIT. Aaron was a PhD student at IIT Madras. We met at a conference and he's a postdoc in France now. Don Daniel was a former postdoc at Los Alamos National Lab. He's a scientist in the same lab beginning this year. So I'll describe some work I did with all these people looking at interaction between waves and vortices in the ocean. So start with a movie which shows, so this is a movie that's showing us the surface speed of the global ocean. So this is based on a global scale ocean model simulation.
Jim, for some reason, we're not able to see. It's showing.
So we're looking at the surface speed of the world's oceans. And this is a model that's forced by atmospheric winds and gravitational tides. So you can see these fast fluctuations here. These are projections of internal gravity waves on the surface of the ocean. And you can see these vortices that are spinning off currents. So these are major currents in the ocean. Gulf Stream, Kuroshio, Gulf, these are all major currents. And of these major currents, vortices spin off due to instabilities known as paraclinic instabilities. So forward the land, continents, and here again you can see these vortices and a lot of these small scale features and fast fluctuations. These are all internal gravity waves. So here again, this is a region where wind forcing is strong. So you can see this blowing effect. So these are wind driven waves. And you can see a lot of these vortices. So this is how the ocean looks. It's a mixture of these fast evolving waves and slowly evolving vortices. So there's a strong time scale separation between these vortices and waves. Near the coast, near the continental shelves, you can see the wave activity is more. So these are regions where tides break and generate more higher harmonics or internal gravity waves. So that's why there's a lot of wave activity near the coast. And so this is how the ocean looks. It's a mixture of these waves and vortices. This movie was based on a simulation that was run at NASA JPL. The data sets are available online for everything that went into the movie. And the point was to show that the mixed ocean is basically a mixture of these fast waves and slowly evolving vortices. The flow is very convoluted. There's 8 to 9 decades of spatial scales involved. So the length scale goes from thousands of kilometers. These are the scales at which the flow is forced by atmospheric winds. And centimeter or millimeter scales is where viscous dissipation of the flow takes place. So the Kolmogorov scale is of order, centimeter to millimeter scale. So energy is being put at these scales and being dissipated at these scales. So 8 to 9 decades are very difficult to resolve numerically. And the time scales goes from order minutes for the fastest waves in the system to order years. So years, this is a time scale of, this is the eddy turnover time scale, long climatological time scale for the vortices that we saw in the previous movie. So the broad set of spatio-temporal scales makes this, resolving the entire flow very challenging. And that's where applied mathematics and carefully planned numerical simulations are required to understand the flow. Now, this is a frequency spectrum that we'll see a lot in this talk. So oceanographers who go to the sea, they put in these instruments at different locations in the ocean. And if you put an instrument at a location and you collect the time series, you perform a Fourier transform of the time series, you get a frequency spectrum that looks like this. So here's a typical frequency spectrum that's collected from the ocean. The x-axis is frequency, and the y-axis is energy contained per unit frequency. The high frequency end here, this is where all the waves are. This peak corresponds to wind-driven waves. This corresponds to tidal forcing, and then there's a whole spectrum of waves called the Garrett-Monk spectrum. So these are all the waves in the ocean. So much higher frequency waves, surface gravity waves, and acoustic waves will all be here at the tip. At the low frequency end here, this is where all the vortices are. This component is called the geostrophic balance component, and this is the slow field. So in the previous movie, we saw these vortices that were slow related to waves. They have a time scale of weeks to a month. And this component is primarily geostrophic balance. If you write down the equations of motion in a rotating frame, this is a Coriolis term. Coriolis term balances a pressure gradient, and this is called geostrophic balance. If you have looked at small scale flows, for example, a flow in a pipe, the flow is perpendicular to constant pressure surfaces, whereas in geostrophic balance, flow is parallel to constant pressure surfaces or isobars. So that's this condition, geostrophic balance. And this is where all the geostrophic balance component lives, this low frequency component. So the internal gravity waves, they have a time scale of minutes to a day. There's a broad spectrum of waves in the ocean. This is a dispersion relationship which connects the horizontal and vertical weight numbers, kh and kz of the waves, with the frequency. So F and N corresponds to rotation and stratification rate of the fluid, and all the waves of frequencies ranging from F to N. So F is somewhere here, N is the buoyancy frequency associated with stratification, it's here. So this is where, this is the frequency range of waves. Somebody drew a line on the dock. The frequency range of the waves goes from F here to N, and this is all the wave spectrum. Okay, and the geostrophic flow lives here. So we'll look at interactions between these two components in this talk. Now this is a movie, so this is a zoom in. So the previous movie was showing the entire oceans. Now we are looking at a small part of the ocean near Patagonia, which is near South America. And when it runs, you will see a close-up view. You can see these fast fluctuations. So these are internal gravity waves projection on the sea surface. You can see how fast these are compared to the background slowly evolving vortices. These are the quasi-geostrophic or geostrophic vortices, geostrophic balance component we saw in the previous slide. And here again, you can see these vortices and fast fluctuations. So,
sorry, question.
Yes, go ahead.
So these are real data or simulations?
Simulation. This is a global scale simulation.
Simulation, okay. Is there also real data which of similar quality or?
No, so these are, this is like three-dimensional data that's evolving in time, but observations from the ocean are, like we saw in the previous slide, like this is how observations look. They are collected at a point. You can get a frequency spectrum. Sometimes you have a set of drifters at different locations. You get some data, but from the ocean, we'll never have anytime soon 3D data that evolves in time. This is very expensive from an observational point of view.
Okay, thanks.
Hello, can you just explain again the F and the N again in the previous transparency?
Yes.
The parameters F and N that you had.
Yeah, so if you think of a rotating planet, F is proportional to the local rotation rate, and N is a frequency associated with stratification. So if you put a buoyant particle in the fluid, N is the time scale, 1/n is the time scale associated with vertical oscillations of the particle. So these are the two time scales set by rotation and stratification.
So capital N will be set by essentially the acceleration due to gravity and the density or something like that.
Right. So it's like vertical derivative of density normalized by gravity. That's it. Square root.
Okay, thanks. So,
okay, so now a popular model in geophysical fluid dynamics, atmosphere and the ocean fluid dynamics is the Quasi-geostrophic equation. So I've written out the Quasi-geostrophic equation here. It's a simple model. It's a one component equation. So you're involving one quantity called potential vorticity Q. Q is related to the stream function by this relationship. So you can see here horizontal Laplacian and vertical derivatives involved. This is essentially a scaled 3D Laplacian. So if you set f = n, this is the 3D Laplacian. So Q is related to stream function by this relationship, and Q is attracted by a stream function by this equation. So you can see how it's very similar to the 2D vorticity equation or 2D Euler. A single component Q is evolved via the stream function, and if you knew Q, you could get the stream function by this relationship, and you could time step this reasonably fast. So this is the quasi-geostrophic model, and it's popular. It was very popular in the geophysical fluid dynamic community because of the simplicity. Instead of integrating the entire Navier-Stokes with rotation stratification, you integrate this single equation model. You don't have to resolve waves, so waves are completely filtered off this model, and it's very fast to integrate. And turbulence that you get out of the system is called quasi-geostrophic turbulence. And so we're looking at a simulation of the quasi-geostrophic equation. This is a certain vertical plane. The initial conditions are random data or white noise. So on every grid point in the domain, I have a random number. And when I evolve this, you will see how these vortices spontaneously emerge. So this phenomenology of energy going from small scales to large scales is called the inverse energy cascade. And this is the opposite of what's known as a forward energy cascade. So in 3D turbulence, energy goes from large scales to small scales. In quasi-geostrophic turbulence, energy goes from small scales to large scale, as you see. So these are schematics showing us that wave number goes from left to right. So low wave numbers are here and high wave numbers are here. Large scales are here and small scales are here. So in quasi-geostrophic turbulence, the geostrophic balance flow sends energy upscale or to larger scales to lower wave numbers with time, as we saw here. In 3D turbulence, in the absence of rotational stratification, this is the direction of energy transfer. Energy goes from low wave numbers to high wave numbers with time. And this is the picture one has from the ocean turbulence point of view based on quasi-geostrophic turbulence. So we'll look at how internal gravity waves affects or changes and modifies this quasi-geostrophic turbulence. So previously, if you go back a decade or so in the ocean, it was believed that the ocean is, it was known that there was a mixture of fast waves and slow balance, but people used to believe that order 100 kilometer to 10 kilometer scales, waves are weak, and quasi-geostrophic turbulence captured most of the dynamics. So that was conventional wisdom a decade or so back. But in this decade, we have a lot of observations, satellite altimeter data sets, and in situ observations that indicates that internal gravity waves can be significantly strong and often can be much stronger than the geostrophic balance flow. So this is a figure from Torres et al. That's showing us global map of the ratio of the geostrophic balance component or the vertical component to the internal gravity wave field. So the energy ratio is plotted here. The main point of this figure is to notice the color bar. Notice that the color bar fluctuates 4 orders of magnitude. Blue regions are regions where internal gravity waves are 100 times stronger than the geostrophic balance component. Whereas red regions are regions where balance flow, the vertical component, is 100 times stronger than the internal gravity wave field. So depending on where you look and the season, so this is during 3-month period, average during August, September, October. Depending on the season and the location, geographic location, internal gravity waves can be significantly stronger or weaker than the geostrophic balance flow. So in these regions where waves are much stronger, quasi-geostrophic turbulence phenomenology that we saw in the previous slide, it does not capture the correct turbulent dynamics of the flow. So that's very crucial. Quasi-geostrophic turbulence, quasi-geostrophic model misses important features in these wave dominant regimes. So that's something that inspired my work to look at how waves change quasi-geostrophic turbulence. And this is important for large-scale models. So large-scale ocean models and climate models, they don't resolve these waves. So it's important that we understand the role of waves so that we can develop better parameterizations for these large-scale models. And so reduced mathematical models and idealized simulations will provide insight into how these waves change geostrophic mode, and quasi-geostrophic turbulence. So this is the outline of this talk. We'll look at 4 different kinds of waves in the ocean. We'll look at wind-generated waves in the upper ocean. We'll look at tides. We'll then look at acoustic waves at small scales. And finally, we'll close with surface gravity waves in the ocean. So this talk is based on these 6 papers of mine, looking at different kinds of waves in the ocean. So the first wave field we look at is called the near-inertial wave. This wave field, so this is the frequency spectrum we saw earlier in this talk. In this frequency spectrum, there's a distinct peak here. This peak is called the near-inertial peak, and it's a peak because winds force the upper ocean at this frequency. So the wind forcing in the upper ocean, it excites waves at horizontal scales of thousands of kilometers. And because you can imagine this wind blowing is essentially like a rubbing in the upper ocean. So the vertical scales are much confined to the upper ocean. Notice the contrast between 1,000-kilometer horizontal scales and 50-meter, order 50 to 100-meter vertical scales. Now, if we take the dispersion relationship of internal gravity waves and we set this extreme aspect ratio, one finds that the frequencies of these waves are very close to F, or the inertial frequency. F is called the inertial frequency and corresponds to the local rotation rate of the planet. So this is a part that makes these waves dispersive, and the dispersive effect of these waves are really weak for near-inertial waves. So oceanographers who collect data in the upper ocean, this is an image that's showing us drifted trajectories in the upper ocean collected over months. Now, typically for a wave field, you will find that these waves will propagate much faster than what you see here. These waves are very slow because of their weakly dispersive effects, and due to that, they stay in a certain region for a very long time. So these are drifted trajectories showing us it's an indication of how slow these waves are. These coils are trajectories, and they stay in a region for a very long time, over months. And this peak, so we look at how this component interacts with the vortices in the ocean. So about 0.5 to 1.
Jim, can I ask you a question? Sorry.
Yes.
So in one of the previous slides, you showed that everything above the equator, the internal gravity waves had about 100 times stronger than the QG motions, and below the equator, everything was red. That means the the QG motion was 100 times stronger than the waves motions. So is it so is it because of the change in the hemisphere? It sharply shows the contrast between the northern and the southern hemisphere.
So this is something that holds only between August, September, October. It changes depending on when you look at it. During these months, the wind forcing and tidal forcing is significantly stronger in the northern hemisphere. So it's something that changes. If you showed you January, February, March, these people discuss that. It's completely different. You will find blue regions here and red regions here. So it's a very seasonal thing, and it also changes depending on the wind forcing. Wind forcing is very strong in the northern hemisphere during these months.
Okay, thank you.
So this particular peak here, it gets up to a terawatt of power, and wind forcing is highly variable, and depending on just like the previous figure and the question, it depends on the geographic location and season. So here's a figure that's showing us the kinetic energy of near-inertial waves alone. So the previous figure was showing us all the waves and the energy ratio. This is a figure that's showing us the kinetic energy of near-inertial waves alone during the same 3 months, September, October, August, September, October. And what we notice is, again, the energy content changes a lot depending on the geographic location, and this is also seasonal. So depending on wind forcing, this is the main point. Depending on the wind forcing strength, waves can be comparable in strength to the vortices, the geostrophic flow, or waves can be significantly stronger than the geostrophic flow. And we decided to look at how these different energy waves interact with the vertical flow. So,
sorry, again, the previous slide, how do you disentangle the energy content of the near inertial waves from the other components?
so it's basically looking at the frequency spectrum. So, oceanographers,
so you just narrow at this frequency spectrum, yes. And then okay, so when people do the observation, so these are observations all around the world at this frequency.
Right. There are drifters at different locations, and they collect all the drifter data and perform a frequency spectrum analysis and truncate near-inertial components. So this particular problem, near-inertial wave problem, we can derive reduced models for this. So the trick is write the velocity field, u and v are the horizontal velocity components. We write this as an amplitude multiplying a fast oscillatory part. So this is the inertial component, and this amplitude equation allows for slow time dependence. So this is a usual strategy in asymptotic analysis. And by projecting this on vertical modes, so these are Fourier modes in the vertical direction, we get a set of equations for amplitude equations for low vertical Fourier modes and high vertical Fourier modes. So these are Schrodinger-like amplitude equations. So you get equations that look just like the Schrodinger's equation in quantum mechanics, and each term in these equations have physical significance. So this is the dispersive term, so the wave dispersion is captured by this term. This term models the refraction of waves by the vorticity. This term models the advection of waves by the vorticity field. And this is again a dispersive term that comes in at higher order than this dispersive term. So these are
yeah. This is the case when the background density gradient is constant. So there's no mixed layer.
Correct, yeah.
Got it, thanks.
So these amplitude equations capture the evolution of waves that evolve according to this equation. And this is an example that shows us the effect of vortices on these waves. So for an illustration, I've chosen an eddy field, a vorticity field that looks like this. Notice how we have two negative vortices and two positive vortices. So the negative vortices are anticyclones and positive vortices cyclones. I have initialized the wave field. So this is showing us the kinetic energy of the waves integrated in the top 100 meters of the ocean. So when I run this, you will see these waves, they accumulate in the anticyclones or negative vortices. They're expelled from the cyclone. So you can see the blue is 0 and red is maximum. The waves are removed from cyclones. They accumulate in anticyclones, so the affinity for anticyclones. And in about 10 days, once we convert everything to dimensional terms, in about 10 days, more than 90% of the wave energy leaves the upper ocean. So these waves are initially trapped in the upper ocean. And if you follow this equation, you can see initially these waves are significantly large horizontal scales. So in this amplitude equation, all these terms, this term, this particular term, this particular term, all these terms involve the derivative of the wave field. So all these terms are small, but this particular term is the multiplication of vorticity and the wave field. So this is not negligible initially. And this particular component in the equation injects spatial scales into the wave field. So interaction with the vorticity reduces the spatial scales of these waves, and that's followed by the accumulation of waves in anticyclone and vertical propagation. So this phenomenon is popularly known as the inertial chimney effect, because these anticyclones act as chimneys that trap these waves and sends them to smaller scales. So the advantage here is capturing these effects with a very simple mathematical model. And this is showing us the kinetic energy in the top 100 meters of the ocean as a function of time. So in about 10 days, the kinetic energy is below 10% in the upper ocean. So in response to the previous question, we did look at effects of having a variable stratification. You can put in a mixed layer, and the qualitative phenomenology is very similar. It's just that having a constant n makes the calculations easier, but you can put in a variable n and the effects are very similar. Qualitative phenomenology.
A question for you. Can you go back one more slide, please? Yeah. So where did you get these equations from? Actually, are they some phenomenological equations, or they're derivable from Navier-Stokes plus forcing terms? Or?
We derive this from the Navier-Stokes. If you take, so Navier-Stokes is rotation stratification after some algebra. It's called the Boussinesq equation. So Boussinesq equations are the parent models for most atmosphere ocean flows. These are derived from Boussinesq equations by using asymptotic analysis.
Okay. All right. Thank you.
So we'll look at two different parameter regimes. The first one is called the comparable wave regime, where wave and vortex energies are comparable. The top movie will show us the evolution of the vorticity field, and this is the wave field. Notice how the waves are initialized to be spatially homogeneous. So red is maximum and it's homogeneous in the horizontal direction. Vertical structure, if you follow this, red is again maximum on top. It's the vertical structure of these waves are exponentially decaying. So as you go into the ocean, it becomes blue and goes to zero. So all the wave energy is initially in the upper ocean, the top 100 meters, and this is the vorticity field. So when I run this, you will see these vortices, they merge and they keep getting bigger with time. So this is the inverse energy cascade seen in geostrophic turbulence. And when I play the wave movie, you will see these waves, they acquire smaller horizontal scales and they propagate vertically. So initially there was no wave activity in the interior parts of the ocean, but the waves propagate vertically and they dissipate in the interior parts of the ocean. This is a figure that's showing us the energy budget associated with this process. Red curve is the wave energy. So waves energy is increasing with time. Black is the vortex energy or the geostrophic energy. So geostrophic flow is losing energy to waves in this particular parameter regime. This figure shows us the energy budget of the wave field. A blue curve is showing us the wave energy dissipation. So in this particular parameter regime, about 70% of wave energy is getting dissipated in the interior parts of the ocean. And all of this was done to get this energy transfer diagram. Near-inertial waves, the arrows, wave numbers are increasing to the right. So near-inertial waves have a forward energy cascade. Energy is going to smaller scales as they propagate vertically. In this process, they extract energy from the geostrophic balance flow. And the geostrophic balance flow is sending energy to larger scales with time. The inverse energy cascade is operational here. So this is the total energy transfer diagram in a parameter regime where wave and balanced energies are comparable.
Excuse me.
Yes.
Can you describe the physical scenarios under which these two will be comparable or one will be much greater than the other?
So it depends on the wind forcing strength. So this is a figure that shows us.
So it just goes back to that thing. Okay.
Yes. So if wind forcing is weak, waves and balance flows could be comparable. If wind forcing is much stronger, we are in this particular regime where waves are significantly stronger than balance flow.
Okay, thanks.
So in this particular parameter regime, wave and balance energy are comparable. Waves can extract energy from balance. So that's the main result of this parameter regime. If we look at cases where waves are significantly stronger than balance flow, this is again the geostrophic vorticity, and this is the wave field. When waves are stronger, you will see that these waves, they destroy a lot of these vortices in the upper ocean. A lot of small scales are generated, some of which dissipate in the upper ocean. And once the waves are propagated down, these vortices, they merge and start getting bigger with time. This is showing us again the wave field. The wave kinetic energy is plotted here. You can see how these waves, they gain horizontal structure and they start propagating vertically. But this movie was run the same duration as a previous movie, but you can see how slow things are now. Much of the wave activity remains in the upper ocean. Some of the waves have leaked into the deeper parts of the ocean, but the waves primarily remain large horizontal scales and have some vertical propagation. So in this parameter regime where vortices are weaker than waves, vertical propagation and dissipation of these waves are significantly retarded. And this is the equivalent figure of the previous slide showing us the energy transfers in this parameter regime. Red curve is showing us the wave energy. So waves are now losing energy to the geostrophic balance components. The balance flow is gaining energy in this parameter regime. The blue curve is showing us the wave dissipation now. We find about 15 to 17% of the wave energy getting dissipated in the interior parts of the ocean. So the main results of this parameter regime is sketched here. Near-inertial waves have a forward cascade again, but it's much slower now. Waves are transferring energy to the balance flow as shown by this blue arrow. The geostrophic balance flow has primarily an inverse energy cascade. As we see here, these vortices merge, but during the early phases, when these waves interact with vortices, as we saw in this movie, a lot of these small scale structures are generated in the initial phase, which results in a weak forward cascade of the geostrophic balance flow. So it's a much more complicated picture for the geostrophic balance flow when waves are much stronger. And one of the features that we see in observations is the trapping of these waves in anticyclones. So we saw that in the first movie that I showed, compare in the near-inertial section, waves getting trapped in negative vortices, and that's something we can explain with this amplitude equation. So this is a Schrodinger equation that models the evolution of these near-inertial waves, and this model has a conservation law that's written out here. So this is a partial differential equation, and the energy associated with this partial differential equation is this conservation law. This is not the physical energy, it's not the kinetic or potential energy or the total energy of the waves, but it's energy that's associated with the partial differential equation. Each term in the amplitude equation contributes one term. So the blue term here contributes this particular term, red term contributes this term, black leads to this term, and the pink leads to this particular term. Angle brackets here denote integration over the whole domain. So each term here has no spatial structure because spatial structure has been integrated out, but each term evolves in time. So the shown here are time series of these different terms in different parameter regimes. This is a particular example. Left here is shown as a stream function of the vorticity field. This is the vorticity field. And we're looking at three particular cases. These three cases are the wave kinetic energy. Left is a case where wave field is large scale. This is a case where wave and vortex fields are comparable. And this is a case where wave field has much smaller scales than the vortex field. And in all these cases, time series of these different terms here are shown. One thing we'll note here is the red curve. The red curve is always negative, irrespective of the parameter regime or the strength of the waves related to the vortex field. This particular red curve is always negative, and it implies that this term is negative. So one can use this conservation law, and you can scale this conservation law and show without numerical simulations. This result depends only on the conservation law. The red term is always negative, and it being negative implies that the vorticity and wave kinetic energy, which is mach tilde base square, is anti-correlated. So anti-correlation between them makes this term negative, and if the vorticity field and the wave amplitude square is negatively correlated, waves should have an affinity for regions where the vorticity field is negative, and that's the explanation for trapping of these waves in anticyclones. So in general, this is observed in the ocean. These are observations that indicate this, and using the simple model, we have an explanation for why waves accumulate and trap in anticyclone in the upper ocean.
There was a question.
Yeah.
Go ahead, Abhishek, after that.
Oh, sorry. So what is the term J?
This is the Jacobian term. It's the advection of A by C. So this would be psi x ay minus psi y ax.
Okay, so this is a nonlinear equation.
The amplitude equation is linear in A. If you know psi, it's linear, but we don't know psi. So once you couple it, it becomes nonlinear.
So the psi, so because you just had an equation for A, right? And so there's a separate equation for psi.
Yes, you have to couple it. So it depends on a lot of complication whether you want to couple it or not. The stream function has a slower time scale than the amplitude. So if you couple it, stream function also starts evolving. So it becomes a fully nonlinear equation. To explain this conservation law, you don't need the nonlinear term. You can just use the linear equation to explain this.
Yeah. So in the previous couple of slides that you showed in these two different regimes, how the energy flows between how you have these two different flows from the waves to the geostrophic flow. So the time scale for this flow is, I mean, there's a natural time scale, which is what you said, this inertial time scale, which is 1 over the rotation frequency. But the time scales for this cascade, or not cascade, whatever, transfer of energy between these different things, this is it parametrically smaller than that frequency? And if so, what is the parameter that sets the relative time scales between the inertial time scale and the time scales for this? And again, I think you had in two different, depending on the different regimes, the left-hand regime and the right-hand regime, I guess they had very different time scales, right?
The energy cascade timescales of waves is something that's it's not often clear. The cascade depends on the interaction rates and all. So for this particular problem, the cascade rate is slower than the inertial time period. So it's comparable to the geostrophic balanced flows evolution timescale, the dissipation timescale, that is. And so one of the points of these simulations was to show that depending on the strength of the geostrophic flow, the wave cascade can change. So that's something that was not known in oceanography. Very recent observation, Wave et al. Confirmed this. What we find, so this slide summarizes the near-inertial dynamics, and that answers the question you asked. The mesoscale ADs, the geostrophic flow, it imprints spatial scales on the waves and it traps in the anticyclones. And the main point of these figures was to show that the strength of the geostrophic flow, it plays a big role in the vertical propagation, forward cascade, and dissipation of these waves in the interior parts of the ocean. So this, in oceanography, these waves would propagate into the interior parts of the ocean and break at small scales and dissipate, and that's believed to lead to ocean mixing. So regions where ocean mixing take place are still unknown and unresolved because observations are very sparse. And Whale et al. Is a recent paper that shows that depending on the strength of the geostrophic flow, they looked at some observations that are available, and they show that depending on the strength of the geostrophic flow, the dissipation rates of these waves are stronger. If you have a stronger geostrophic flow, it accelerates the forward cascade of waves. Whereas if you have a weaker geostrophic flow, the forward cascade of waves are significantly weaker. And the energy transfer direction is also something that came out of the study. In parameter regimes of wave and geostrophic flow are comparable, waves can extract energy from balanced flow. Waves stronger than geostrophic flow, waves would transfer energy to geostrophic flow. So in oceanography, usually they don't have data sets that are good enough to capture the energy transfer direction. So these are almost impossible from observations. And using numerics, we are able to get these energy transfer directions.
Yeah, and my question was more about that energy transfer, the fact that you have these two different vertical, I mean, one going the other way compared to the other. The time scale for that transfer was, is that something you...
Oh, the blue, yeah, the blue is faster. I thought you were asking about the red. The
no, I was asking about the blue. The blue
would be faster.
But in the other one, it was much slower, right? In the right-hand figure.
This one, it's slower, yes.
But so slow compared to the inertial time scale.
Correct.
So I see. And does one know what sets that? Because the relative, the ratio of that inertial time scale to this time scale, what sets that parameter?
The ratio of geostrophic to wave energy is what sets the ratio.
I see. That would set the time scale for the, I see. So that's why it's simply just that, just the ratio of the energies. And one can, I mean, this is something you can show just by some scaling arguments or something?
From the simulations, yes.
Okay.
So that summarizes the dynamics of near-inertial waves in the upper ocean. We'll now move on to the second dominant wave field in the ocean. So in the first movie that we watched, I showed you this global scale simulation. Tides are the second dominant waves in the upper ocean that we saw in that movie. So in the frequency spectrum, this is the typical frequency spectrum that you see in the ocean based on observations. The wind-generated near-inertial peak was here. So this was the previous part of the talk. Now we'll move on to this particular peak, which corresponds to gravitationally generated tides. So as you all have learned in high school, because of moon's gravitational force, we have tide. So this is what sets the tide. Because of the differential gravitational force, the oceans and the land surface swells up. This is called the barotropic tide. The ocean swell is significantly higher than the land swell, and because of that, its tides are mostly associated with ocean, although land surface also swells up a little bit. And the initial tide is called the barotropic tide. So this is a figure that's showing us the tidal budget of the entire planet. Moon contributes most of the tidal budget. Solar tides, as you can see, is about 0.5 terawatt, whereas lunar tides are about 3.2 terawatt. M2 component is the dominant tidal component. So in the frequency spectrum that we saw earlier, this frequency spectrum, if you really stare at this frequency spectrum, you can see distinct peaks that are much weaker. There are O1, K1, 2, M2. These are all weaker tidal component. The M2 tidal component is the dominant one and puts in about 2.5 terawatts of the 3.2 terawatt that's contributed by moon in total. A lot of this tidal energy gets dissipated in the atmosphere and the land. And of this 2.5 terawatt, about 2.4 terawatt gets into the ocean. And obvious question is, where is all this energy getting dissipated? If the oceans are in equilibrium, the 2.4 terawatt that's getting into the ocean must be dissipated to maintain that equilibrium. So this question that has to do with the dissipation of these tides. This was first looked at by G.A. Taylor. So as many of you would know, G.A. Taylor was a famous fluid dynamicist. Taylor looked at a lot of problems for the first time. So this is one of the problems that he looked at for the first time in the fluid dynamic community, tidal dissipation. So Taylor, he made an estimate for the dissipation of barotropic tide in the Irish Sea. So Irish Sea is a shallow oceanographic region, and Taylor, usually using fluid dynamic drag calculations, he made an estimate for the dissipation of tidal energy in the Irish Sea. And then Jeffries, a year later, he extended his calculation for many shallow oceanographic regions that were known at that time, and was widely believed that most of the tidal energy input into the ocean is dissipated near shallow oceanographic regions. This was conventional wisdom for a very long time until relatively recently. The TOPEX Poseidon mission, this was a landmark satellite mission, joint mission between United States and French space agencies. This mission was landmark in oceanography because this provided oceanographers satellite altimeter data sets for the entire ocean surface. So the entire ocean surface, or the surface topography of the oceans, could be mapped. And Egbert and Ray, these guys were at NASA, they used a model known as Laplace tidal equations, and they predicted that up to a terawatt of power. So the 3.2 terawatt that gets in, up to a terawatt of tidal energy gets converted in the open oceanographic region. So this is the first paper that they wrote in Nature explaining this, and a lot of subsequent papers appeared that provides better estimates in this. But the conventional wisdom now is shown in this figure. Tides, the barotropic tide is basically a tidal component that has no vertical structure. So it's like a flow that goes like a slab of fluid. This crashes against the seamounts and generates a lot of internal gravity waves. So in regions where the tidal conversion, this process is called the tidal conversion. In regions where tidal conversion takes place, internal gravity wave energy is significantly higher than the vortex mode or the geostrophic flow. So this is what inspired us to look at how high energy tides would modify geostrophic turbulence. So we're using a model that's written out here. This is a model that's obtained by projecting the full 3D equations onto the barotropic, which is the zero Fourier mode, and baroclinic, the first baroclinic mode, first Fourier mode in the vertical direction. And we do this because in the ocean, a lot of the balanced energy or the geostrophic energy is associated with the barotropic and the first baroclinic mode. And internal tides have a lot of energy. Most of the energy is in the first baroclinic mode. So this reduced model captures the tide balance interactions. This is a schematic that shows us the model. The barotropic flow and the baroclinic flow, these are the balanced components. And this is the red box shows the tidal component. This figure shows the energetics associated with the transfers in the absence of tides. So this is, if you didn't have tides, no waves, the interaction between these two components are shown here. Purple curve is the energy of the paratropic flow. Green curve is the energy of the paraclinic balance flow. So energy transfer is from the paraclinic balance to paratropic balance. And this is the two-mode quasi-geostrophic turbulence phenomenology. It's a very popular model in the geostrophic turbulence component because two modes resolve most of the balance dynamics. And we're trying to understand how the tidal component, or the red box here, affects this. So we'll look at two movies here. This is showing us the geostrophic vorticity field. In top is a case where waves are not existing in this setup. So this is geostrophic turbulence. Bottom is for a case where tidal energy is significantly higher than the geostrophic vorticity field. And the main feature here, after a long time, you see this vortices here, they merge, they keep getting bigger with time. Whereas here, high energy tides can prevent it. Just like we saw for the near-inertial case, a lot of these tidal energy components can prevent vortex mergers and formation of large-scale coherent structures. So after a long time here, we have well-defined domain-scale coherent vortices forming. Here, we just don't form these large-scale vortices. And once we look into this energy transfer details, what we find is these internal tides, they transfer energy to the balance flow in these high tide or strong tide regions. And that energy transfer is what breaks these coherent structures. So in quasi-geostrophic turbulence, we have multiple conservation laws that leads to the inverse energy cascades. When you have a lot of these waves, conservation of energy for the geostrophic flow breaks down because of the energy transfer from waves to balance, and that's what generates these small-scale structures. So that's the brief peek into a strong tide balance interactions. In the presence of high energy tides, waves or tides can transfer energy to the vortices and can break these vortices. So this is left as the case. If you didn't have tides, strong tides can do this. And this is very important because effective turbulent diffusivity is significantly higher in these regions compared to these regions. So we're looking into how high energy tides can modify turbulent dynamics and diffusivities of these strong tide energy regimes. So this is a schematic that shows energy transfers in these regimes. And this is very useful for developing parameterizations for these ocean models. So the details, the flow details and the energy transfers in these high tide regions were written out in this paper. You should take a look at this if you're interested in knowing more about these transfers. Third part of this talk is looking at acoustic waves. So now we are at really small scales, and the inspiration for this comes from experiments at small scales. So, if you looked into fluid dynamics in general, measuring quantities, properties of flows in general is very difficult without disturbing the flow. So non-intrusive flow diagnostic techniques are a set of techniques that are actively being pursued where you try to measure the properties of the flow velocity, temperature, density, and so on, with significantly low influence on the flow. So you don't want to intrude the flow. And one of the techniques that was suggested that was very popular in the 90s, this was introduced in the 90s and was very popular then, it's by sending in very high frequency acoustic waves. So you send in ultrasound waves, and these ultrasound waves will be scattered by the vortex field, and by collecting the scattered wave field, you can predict vortex structures in the flow. You can deduce whether it's a single vortex or you have a dipolar structure and so on. And the inspiration for this work was that in most of these cases, the wavelength and the horizontal scale of the vortices are comparable. So lambda is the wavelength of these acoustic waves that are being sent in, and L is the vortex scale. And most of these experiments are in cases where lambda by L is order 1. Whereas if you look at asymptotics and theory that exist, ray tracing or WKBJ is a popular technique which works when the wavelength of the wave field is significantly smaller than the vortex scale. The opposite extreme is the case where wavelength of the waves are significantly higher than the vortex scale. That's called the Born approximation. And these are the two popular asymptotic regimes, the theoretical regimes in which you can derive a reduced model. Whereas in most of these cases, where observationalists or experimentalists are looking for models, we usually in the parameter regime where lambda by L is order 1, wave and vortex scales are comparable. So that's what inspired his work. Most of the experimentalists, when they write papers, they say, we are in this particular regime, but there's no reduced model in this particular regime. So we'll use either this or this, even though both of these are really invalid. So that's what inspired this work and this paper. I was able to derive an amplitude equation for this particular regime, and I'll show an application of this. So this is a model. The small parameter in this work is the Mach number, which models the ratio of fluid velocities to the speed of sound. So Mach number is small, and after some massaging, we get the equations into this form. Primes denote the wave field, and uppercase letters denote the vortex field. So this V is the vortex field. By substituting in pressure and velocities in this form, so it's an amplitude multiplying a fast oscillatory part. This is the acoustic frequency omega. Omega in non-dimensional form is related to the wave number by this relationship. So every wave number that has the same magnitude has the same frequency. So that's the peculiarity of acoustic waves dispersion relationship. And this is an amplitude equation that captures the evolution of these waves in the vortex field. So uppercase V is the vortex field. This is the interaction term between the wave and vortex field, and the amplitude evolves according to this equation. So here's an illustration of this scattering of acoustic waves by the vortex field. This figure shows the vortex field. It's a turbulent flow. Here is the vortex field laid out. This is showing us the top view, and this is the spectrum. Initially, I'm sending in a single wave, so it's a plane wave that looks like this. You can see the phase lines here. On top, you can see the phase lines. It's a single wave, due to which you can see these dots in spectral space corresponding to kx1, ky0, and kx-1, ky0. So this corresponds to cosine kx minus omega t in physical space. So now when I send this in, you will see these acoustic waves being scattered by the vortex field. So you see these inhomogeneities being generated in the wave field. And in spectrum, you can see the scattering transfers energy to other wave numbers. So you form this ring. And as we saw earlier, the frequencies of these acoustic waves are equal to the magnitude of wave number. So all the wave numbers that lie on the circle have the same frequency. And due to this effect, the scattering by the vorticity field excites other wave numbers that lie on the circle. So this circle or ring gets lighted up in spectral space as these vortices scatter the wave field. This is a figure that's showing us a comparison between the amplitude equation and the pattern model. So plotted here is the angle. It's an effective angle in spectral space that captures the scattering. So higher the scattering effect, higher will be this angle. Blue curve is from the asymptotic model, and the black curve is from the full set of equations. And they agree for reasonably large Mach numbers. So up to about 0.3, the agreement is good, and beyond 0.3, the small parameter, the amplitude equation starts to diverge from the pattern model. So if you have a small parameter, yeah.
Is the vortex field not affected by the wave field?
Yeah, in this case, the vortex field is frozen. The waves are much faster, so the vortex field is not assumed to evolve.
I see.
So this is a comparison.
Fluid,
yeah, go ahead.
Is this a homogeneous fluid, a constant density fluid?
It is. It's at much smaller scales where density changes don't matter.
Okay.
So that's a comparison between the amplitude and the pattern model. So if these waves, so this is a parameter regime where the acoustic waves are really, really weak, as in the application. So usually when they send in these acoustic waves to scatter from the vortices, wave amplitudes are orders of magnitude smaller than the vortex field. And the vortex is considered to be significantly slow. It's pretty much steady. And this is an extreme example. For simpler cases where you have a few vortices, amplitude equations are very good substitute for the full set of equations. So the last part of this talk, we'll look at surface gravity waves.
Sorry, can you please show that amplitude equation again? So So if I understood right, so so now this is you're freezing the vorticity field, and now it's just a linear differential equation that you're, you're solving it sort of like it's like some kind of a heat equation type of thing. Is that how you're solving it?
Vortex field is frozen, so it's a linear equation, and it's heat equation with an I in it, so that makes this a Schrodinger equation. Things don't diffuse like the heat equation, but propagate. So it's the I makes it dispersive, and yes, so it's a model that captures the scattering of these waves by the vorticity. So usually, in these observations, what they want is the process itself is really fast. You send in an acoustic wave, it's scattered, so the whole thing happens between a few wave periods. So things are much fast, and this example that I showed you is a very extreme example where we run this for a really long time. In reality, for applications, you would look only at a few wave periods or so.
And is this equation a standard equation or it's novel?
It depends on how we define novel. It's a typical Schrodinger-like equation. For this particular application, it's a new equation.
Okay, so like for acoustic waves scattered by eddies, like this is how you've modeled it, and it's not happened. It's not been written down in this way before.
Right. So no, I would say this was the first amplitude equation for acoustic waves. Nobody has derived an amplitude equation in this particular parameter regime. So ray tracing is an example where you can write down simple ODEs. Born approximation is the other limit where you don't have an amplitude equation. In this particular parameter regime, this is the only amplitude equation that is known for acoustic waves.
Okay.
And where did you use the fact that this epsilon is a small parameter? I mean, it appears in this sort of singular way in the differential equation, right? And so is that, so did you do some perturbation around this
Yeah, so epsilon is used for the asymptotic analysis. So we substitute. So this is a starting point. We substitute in these ansatz, and pressure evolves according to amplitude and this. And once you substitute in this, you use multi-time scale asymptotics, and after some averaging, you get to this equation.
Yeah, but in the equation itself, this epsilon appears in this sort of way.
Right. Yes. So that's what makes this equation special. So these are non-standard asymptotics. So this technique is called reconstitution. You wouldn't capture these terms by standard asymptotics. So this is it's a long discussion. What happens is, in usual asymptotic analysis, you have to write down a solution of the leading order equations to do asymptotics to the next order. This technique does not write down a solution. What you do is you say, I want an amplitude that has spatial structure. So A here depends on space and time. And so you substitute this into these equations. You write down the epsilon power 0 equations. You get a set of equations. You don't write down a solution to that equation system. You carry on to the next order. You collect resonant terms at the next order, and you collect them all together. And that's what leads to this particular term. So this term is asymptotically very small, omega square plus Laplacian, because if you follow this dispersion relationship here, omega is magnitude of epsilon. So if omega is exactly equal to magnitude of epsilon, if this is an exact equality, this term would be 0. Okay, so it was already here. Omega k makes a 0 go to 0, but omega is not exactly equal to k. It's near resonant, which makes this small. Epsilon is small, so that makes this an order 1 term.
Nice. And so you actually did this, you could do this analytically to some extent, and then you compared with the simulation. I mean, so I was just missing what you showed on the next slide. That was supposed to be a comparison between the simulation and some analytic thing that you could extract from here.
This slide doesn't have anything analytic, because the amplitude equation still is a variable coefficient PD. So there isn't an analytic solution, except for special cases. So in the paper, I have a few special cases. If you assume a simple vortex, you can write down analytic solution. But for flows like this, there's no analytic solution. So this is a comparison between the parent model, which is from the black curve, and the blue curve is from the asymptotic model.
Oh, I see.
I have a question.
Yeah.
So actually a couple of questions. First one, where did you use lambda by L is order 1?
When we retained all these terms, so if you follow this, right, you have v prime dot grad v and v dot grad v prime. Usually what is done is, depending on this ratio, you retain whichever term is order 1. So
you can go to the ray tracing limit and the Born limit from this model?
Yes.
And
that's something we show in the paper. It's
I see.
You can extract both regimes.
You can abstract both regimes. I see. Picking up on this question that you just discussed with the sort of inconsistent or non-standard asymptotics, you said you didn't find a solution to the linear problem. Doesn't that imply that you have to then track the linear solution as well? Otherwise, how is the equation for A evolved? It's just a secularity condition. To get the full solution, you would still need the lowest order term, right?
Yeah, so the lowest order terms are written here. Pressure is amplitude. This is the lowest order.
Yes.
It is the solution. So if you substitute in A is a plane wave, e power I k dot x, you would get an exact analytic solution. But we don't do that to get the amplitude.
In that case, I would end up with like a standard, in that case, would I end up with a standard NLS amplitude equation is what I would, and the coefficient would be like omega prime. That's what I would get.
Yes. So the problem with that is you are capturing a single wave number. That's a problem with NLS. You are only capturing the evolution of a single wave number. We don't want to do that. We want to capture all the wave numbers that satisfy this criterion, everything that lies on and around a ring in spectral space.
Right. I see. Okay. So in principle, whenever I derive an NLS from another model, I can do this?
You can do this in any case. The problem is you'll have to check whether the model is valid. In NLS-like situations, what we find is you would generate higher harmonics and so on once you have more wave numbers, which means the amplitude equation quickly goes out of phase with the full model. So that's a problem.
So put it another way, in your case, it's because your perturbation equation, the boxed equation at the top, is actually linear, that you're not generating higher frequencies.
Yeah, so the advantage here is that the acoustic waves that are being sent in are orders of magnitude weaker than the vortex field.
Gotcha. Right. And maybe I misunderstood, but the overall goal was to somehow sense the vortex field based on these acoustic waves, right?
That's the goal of these observationalists. And what I showed here is an extreme example. Usually their cases are simple. They have a few vortices or dipolar structures. So in that particular case, if you know the wave field that's coming out, you can reconstruct the vortex field to some extent. So that requires using this amplitude equation.
Right. So I guess you're suggesting I do an inverse problem for the amplitude equation.
Correct. Yeah.
Got it. Cool. Thank you very much.
So yes, the last problem, I'm almost done. Last problem is looking at surface gravity waves. So the setup here is we're looking at the ocean near the coast now. So think of the beach. This is the deeper parts of the ocean, and this is the beach. So wind excites surface gravity waves in the deeper parts of the ocean, and they propagate in different directions. Some of these waves, they make it to the shore, and as they near the shore, refraction by the shore leads to the wave fields getting modulated. They become nonlinear, and they eventually break and dissipate here. So turbulent mixing takes place here. So for this particular problem, we are somewhere here where the waves are starting to get refracted by the bottom topography. So this figure shows a schematic. The zeta, for the previous problem, zeta was a vorticity, but now it's a topography. And we're trying to understand how topography can refract waves when the waves are still linear. So before nonlinear and wave breaking takes place, can we get a model for the initial phases where the waves are getting refracted by the topography? And the inspiration for this is a lot of communities have applications for this. One is shore protection. So often, the shore protection community, they like to have setups near the shore where you can refract and deflect incoming waves without them making it to the shore. So can we design structures to put in the shore where you can refract and deflect waves? And also renewable energy harvesting is a big thing where people like to accumulate these wave energy in specific spots. So the problem with surface gravity waves in general is that these waves are everywhere and they're all over the place. And so their amplitudes are small, but they're everywhere. So if we can focus these waves to specific regions near the coast, we can have these renewable energy harvesting devices and extract energy from these local spots where energy is high. So again, the idea is to derive a reduced model without having to integrate the full set of equations. So the full set of equations for this problem is written here. So a lot of you might have seen this in fluid dynamics classes. This model is popularly derived because surface waves are way more easier to visualize than internal gravity waves. So it's this model you might have seen in different places. For this particular case, there's no vorticity. So the flow is potential. Phi gives a potential. The top surface is eta. So we have two boundary conditions on the top. This is a dynamic boundary condition. So it's basically Bernoulli's equations on the top surface. This is a condition that demands that the top surface remains a material surface, that you don't develop spontaneously holes in the free surface. At the bottom, we have this condition, which is basically impenetrability. So at the topography, the fluid can't penetrate the topography. So these are the equations. The equation itself is linear. It's Laplace's equation. The nonlinear boundary conditions is what makes this problem challenging. You have to integrate these equations with the nonlinear upper boundary condition. So eta on the moving free surface, you have this nonlinear boundary condition, and that makes this problem stiff and difficult on a relative sense. And again, here the trick is if you have a small parameter. So in this particular problem, small parameter is the ratio of the topography to the mean fluid depth. So we are in the initial phases where the waves starting to get refracted by the bottom topography. And we are also assuming that the waves are linear. So the nonlinear wave breaking, we are far from nonlinear wave breaking and turbulence. And if these conditions are satisfied, one can again derive an amplitude equation that looks like this. So A is the amplitude, and this is the term where topography refracts the wave field. And the advantage of this amplitude equation is for the problems where these conditions are satisfied, you can integrate this amplitude equation 100 times faster than the full set of equations. So that's a big advantage. We compare these fully nonlinear equations with the amplitude equation, and under the conditions here, you can integrate this multiple orders of magnitude faster. So the amplitude equation is very useful for a lot of applications. I'll show one application here, and this has to do with wave focusing. So think of topographic features that look like this. So from classes in optics in high school, you would know that if you send in a light ray, and if you have concave mirrors, you would focus light rays at a focal point. Now, in a similar way, you can design topographic carpets that look like this. So you send in waves from here, going from left to right. These waves are reflected and they focus at a focal point. So the idea is, this is the configuration that has been suggested for these renewable energy harvesting community. You design these kind of wave carpets, put it in these coastal regions, and you can get high wave energy in focal points, and you put in these renewable energy harvesting devices at these focal points to extract energy more efficiently. So this is a movie that's showing us a comparison between the amplitude equation and the fully nonlinear equation. So top here is the 2D view, physical space and spectral space of the amplitude equation, and bottom is the amplitude, the parent model, the fully nonlinear surface water equations. And this is a 3D movie that shows us the focusing. So when I run this, you will see waves are going from here to here. They get refracted and they focus at this point. You can see wave focusing and increase in the wave amplitude with time. So in these regions where wave focusing takes place, wave amplitude can be 5 to 10 times higher than the usual locations. This is a figure that's showing us the comparison between the amplitude and the fully nonlinear equation. So the black is from the fully nonlinear equations and red is from the amplitude equation. Plotted is the amplification we get at this focal point. So up to this about 0.35, we get pretty good agreement between the amplitude and the full set of equations. So this is a comparison.
Can I ask you a question, please?
Go ahead.
Yeah, so can you just go back in your slides? So there are these complicated equations on the left-hand side with these moving boundary conditions. And on the right-hand side, you have a much more simplified model. Is there some understanding how you go from the left-hand side to right-hand side, or it's just something phenomenological that you have done in the box on the right-hand side?
It's again asymptotics. So we use this asymptotics. The small parameter is this zeta by h.
Yes.
And you just go through multi-time scale asymptotics. You remove resonant terms, and using secular conditions, you get this amplitude equation.
I see. So there is a derivation from the left-hand side equations with co-moving boundary conditions. I'm particularly interested in that part, actually, how you got around to treating those boundary conditions.
Yeah, so I mean, yeah, the boundary conditions, you substitute this in, and this can be solved. So you write down a solution, and then you basically use Green's identity. So you use Green's identity in 3 dimensions, and when you use Green's identity, you get contributions only from the boundary terms. So these boundary conditions leads to this amplitude equations.
I see. Okay.
And that's
okay, good.
This paper explains all the procedure.
Okay. Thank you.
So when you come very close to the coast, or you have a very complicated boundary, how good is potential flow approximation itself? Like you'll get lots of vorticity generation, right?
Yeah, so in this setup, we are away from the steep topographic regions. So surface waves, so when they're generated, winds excite these surface waves. There's a lot of turbulence and wave breaking happening here. Some of these waves, they propagate away from the nonlinear regions. A fraction of them makes to the shore, and in a phase where they are not really close to the shore, where there's a lot of vorticity generation turbulence, before we hit that phase, that's a phase when the vorticity effects are weak, and this model. So this model is really popular. If you followed wave turbulence, the wave turbulence community thrives on this model. So you're away from vortex field, and if you put in vorticity, things becomes way more complex because now you have 3D Euler with a free surface. So it's a lot more complicated.
Is that where you want to do this wave focusing and things? I thought you wanted to do those closer to the coast.
No, we're not really close. So again, so it depends on the application what we want. If you really want to model it near the coast with vorticity, you have to integrate the full equation. There's no alternative 3D Euler. But if you're a little away from the steep regions of the coast, where the wave field starts getting refracted, you can use a simpler model. So simple models comes at a price. You have to satisfy these conditions.
Thank you.
So yeah, so this is the comparison between the amplitude and the full equation. So if you satisfy these conditions, we get pretty good agreement between the amplitude and the full equations. Yes.
You're showing a case where the incoming wave has only one wave.
Yeah, for this particular example, yeah, it's a single wave number to start with.
What happens when there's multiple wavelengths coming in? I guess you're assuming the nonlinearity is so small that
you can have multiple wave numbers, so you can have an entire spectrum.
You don't have wave. I see. I see.
You can allow a spectrum of waves, and that would be okay. We just, for this particular example, it's an extreme example where I'm trying to show that a single wave can be focused at a point. When you have multiple waves, they would already have some interference at some points. So this is a case where there's no.
Yeah, I wanted to know what the efficiency was in that case.
Yeah, so you can have a spectrum of waves and they can interact.
Okay.
Okay, so that sort of concludes the talk. So I've been trying to show that the ocean has a broad spectrum of waves, and depending on the parameter regimes, sometimes you will be able to use reduced mathematical models. You can derive them using asymptotics. Waves can extract or transfer energy to the balance source. This is one of the important things that came out of my study. In oceanography, usually people like to think that internal gravity waves in general would just extract energy from balance flow, but we were able to show that energy transfer can be both ways. It's not one way. Quasi-geostrophic turbulence, it does not apply to many oceanographic regions. So this is another thing that we changed. At mesoscales in the ocean, 10 to 100 kilometer scales, it's widely believed that quasi-geostrophic turbulence would work, and you would get a first prediction of what happens in these regimes using quasi-geostrophic turbulence. But as I showed in wave-dominant regimes, the phenomenology is very different. You need to keep track of these waves to understand the turbulent dynamics of the regime. And these wave-dominant regimes are still very open. Large-scale models, ocean models, and climate models don't capture these regimes because they don't resolve waves. So understanding the wave-dominant regimes will help in developing better parameterizations for large-scale models. And in general, a lot of these processes are nonlinear, but under very special circumstances, if conditions are suitable, one can derive simple mathematical models. And when you derive simple mathematical models, they're useful in time stepping because you save a lot of computational resources, and you get a lot of phenomenological understanding without having to rely on complex models. So that's Sander's talk. Thanks a lot for attending, and welcome all kinds of questions.
Thank you so much, Jim. Questions? People can just unmute themselves and ask a question.
Yeah, I have one question, Jim. This in the entire talk, there's something about temperature actually of the ocean. I did not see any such parameters. So I mean, if water is very cold or very warm, I guess there would be a difference in the parameterization of these equations, right? Or am I missing some point here?
Temperature enters through buoyancy. So temperature is related to buoyancy, and the Buzynsk equations, the variable that captures temperature affects buoyancy, and buoyancy appears in the equations. So we're starting with equations that have evolution for velocity and buoyancy field.
I see. Okay.
Other questions?
Yeah, so I had a question on this. So you showed this power spectrum, which is from observation, right?
Right.
And so do this like for example, the simulations kind of also reproduce this power spectrum, and do any of these four theories you said, do they actually capture any part of the spectrum?
So each of the problem was looking at specific wave fields. So these different wave components do different things. And depending on where you look in the ocean, some of these waves are more dominant than the other. So now at this point, if you follow ocean models, they resolve up to here, the spectrum. The best ocean models resolve up to here. And the high frequency end is called the Garrett-Monk spectrum. This is still not captured by even the best high resolution simulations that we have now in ocean modeling community. So like I said in the beginning of this talk, the entire flow has 8 decades of spatial scales and time scales. So it's very difficult to capture all of them. And that's where applied math and careful planned numerical simulations comes in. So we're not at a computational position to resolve the entire frequency spectrum in space and time.
Okay, so you can go up to till 0.2 cycles per hour, the ocean models.
It's about a decade. A decade or so can be resolved at this point. So the large-scale ocean models climate models and all, they only resolve the low frequency in this one because they have to integrate very long time scales, decades, like climate models, right? You're looking at decades, centuries of simulations. You can only resolve this end, so you don't capture waves at all.
Okay, so there's no understanding of why you get this power, which is like very close to -2 in this high frequency.
That's something I'm working on now. So the next paper will be on that. What sets the Garrett-Monk spectrum? So this is another open question, Oceanography. We're looking at using theory and numerics. So the next paper I'm writing will be on that. What sets -2?
Okay.
I mean, there isn't, sorry, but for this -2, there isn't even a sort of soft phenomenological theory to explain, because it's a nice number to, something where you balance terms dimensionally, something of that sort. So there's no way. So it's just observation that it's -2. Is that it?
Because it's a nice number, there are a lot of theories. Using wave turbulence, there are a lot of theories, but all these theories exclude the geostrophic balance component. This component is excluded in all these theories. If you have this component,
that I understand. If it's a multi-scale thing, so one can separate. But for example, if I look at some sort of weak / wave turbulence interactions with 3 interactions, 5 interactions, so some of them might give a -2, right? In the sort of large frequency case, or
they do, yes. But they all ignore the geostrophic flow, the vertical component.
Right.
And the vertical component is very important. That actually, what we find is that sets the -2. So, right, if you looked at numerics too, so the wave turbulence community, they don't look at numerical simulation carefully. If you have only wave interactions, the time scales of these things are very slow, and you don't get a -2 if you integrated the Bussinesque at really high resolutions without the vortex mode. That is, so you need the vortex mode. That's the important message.
So in this last part of your talk, you had a very nice, demonstration of this wave focusing. So to go back to the first part, like where you talked about you called it chimney effect, right? The trapping of waves by the anticyclonic vortex. So there, is there a simple physics words way of explaining why that happens?
The anticyclone trapping. Yeah. So we do using the model, we were able to explain this trapping using the conservation law. So it goes to showing. So again, this is again a long explanation. What we do is you take this conservation law, and you can scale this conservation law in different parameter regimes. And by scaling, you look at the dominant balances. So for example, this is a case where wave field has much larger scale than the vortex field. So in this particular case, the black term and the pink term drops off. The dominant balance is between the blue and red. So blue plus red is almost 0, which means red is equal to negative blue term. Blue term is a positive definite term. You can see it's absolute value of grad S square. And because this is positive, red becomes negative definite, and therefore the vorticity field and waves are anticorrelated.
Okay, so you choose one sign of vortex gets chosen because of that.
Yes.
Yeah, okay. That's nice.
So can I ask a question? If we go back to that power spectrum, there's this... yes. So there's this place where it sort of bends upwards. Is there a way to understand why that should happen? That seems a little anomalous in some way, isn't it?
Here?
Yes.
Well, it goes with forcing. This is clear even when you look at simulations, numerical simulations. If you force at a certain scale, wave number or frequency, you would see a peak at that forcing scale, and that's what's happening here. This is a scale that's directly forced. Winds are forcing here. That's what's leading to this peak. Same here.
So that I see. So you're saying that this is a sort of a much more broadened peak really that's where that whole thing, it's unlike the M2 peak, which is very sharp, this is a very broad peak because it's somehow this vorticity scale is somehow more spread out in some way. Is that roughly how to think about it?
Yeah, the tidal peak is way stronger and narrow because the tides have a very well set time scale. This has a time scale of 12 and a half hours. It's 12 hours and 25 minutes. It's a very specific time scale.
Right.
So that's why it's like a delta function. Whereas wind forcing, it's close to F, but it changes a lot. So it's more spread because the forcing frequency is not very well set. Tidal time scales are very well set by lunar gravitational forces.
Right.
So it's a more specific number.
Yeah, no, that I understand. But here you're saying it can go over like 1 order of magnitude, which is why it's roughly almost 1 order of magnitude the width of this other peak.
Right.
So it's more okay.
Any other questions?
Yeah, one sort of very broad type of question. I mean, since you study this type of very impactful area, I mean, what is the, climate change is a very big issue today facing all of us. Where does this type of work fit into that scenario, if that's at all a meaningful question to ask?
Yeah, so going to climate models have, they resolve only this part. So none of these are resolved. So if you understand how these affect this component, we can develop parameterization. So when you write down the equation for this component, you say, now I want to model all the small scale stuff that's not resolved using extra terms which are prescribed. So that's, if you looked at LES, large eddy simulations, this is a philosophy. You don't resolve scales underneath a certain scale. So you parameterize them, and that's the way to go. So climate models require developing parameterizations for unresolved scales, and that's where all of this would contribute towards.
I see.
So to continue that, in the oceans, is it well known that there are problems with parameterization at present?
Yes, there are. So, for example, if you look up the oceanographic modeling, the diffusivities is a big problem. How do you set diffusivities of tracers, oxygen, nitrogen, and so on? There are two kinds of diffusivities. One is lateral diffusivity, which is associated with constant density surfaces, or the horizontal, and vertical diffusivity is the other thing. Both are set by ad hoc means. Vertical diffusivity especially is set by a simple linear relationship connecting stratification and so on. If you compare simulations that resolve a lot of scales with these ocean models which have set diffusivities, the difference is very big. So diffusivities are way off in these large scale models.
Okay.
So again, on that sort of direction, are there any specific features of the geographic neighborhood of India which enhance some of these effects, or which might play a role in in understanding better the monsoons and so on? Are there? You showed Patagonia had some remarkable vortices and also near the Caribbean, I think. But are there similar things around in the broad Indian neighborhood?
Bay of Bengal has a lot of interesting things going on. There's a lot of recent interest in that region too. It's been observed that the diffusivities of tracers are different from what's predicted by quasi-geostrophic turbulence and all in these Bay of Bengal regions. So there's a lot of data coming from Bay of Bengal, which would lead to interesting work. I don't know enough to say about monsoons. So monsoons, I'm not sure how it affects, but definitely in the Indian neighborhood, Indian Ocean, there's a lot of interesting data which could lead to a lot of interesting work.
Any other questions? Okay, it's been a really nice talk, Jim. You took us through 4 different kinds of things and showed us what all you can do, like with simple models. So thanks very much for your talk.
Thanks to everyone.
Yeah, thank you, Jim, for also patiently taking all the questions. So we hope to have, we hope we will be in touch with more interactions and so on. Yeah.
Thanks to everyone.
Okay. Bye, everybody.